ready for some gamma ray science? Let's get a burst of applause to Rachel. And you have to be feel very, very proud to be here today because she is one of the organizers of this activity, Astronomy on Tap. Was the first one who started this. So you should be very proud to be here today. So Rachel Hamburg. So she's a postdoctoral researcher in gamma ray astrophysics, working in CNRS at the IJCLab on the Université Paris-Saclay campus. Okay, it's just love. Yeah. Okay. She obtained her bachelor's in physics from the University of Arkansas, so she's American, and her master's and Ph.D. in space science from the University of Alabama in Huntsville. So Rachel specializes in gamma ray burst studies, particularly their connection to binary neutron star merges and gravitational wave emissions. So she's a member of the NASA Fermi Gamma Ray Burst Monitor Instrument Team and the SVOM satellite project. Yeah. Woo! So Rachel will explain gamma ray bursts, highlight notable cases, and illustrate the importance of understanding them in the high redshift universe. So let's celebrate
Rachel! Thank you. Can you all hear me? It's okay? All right. So yes, thank you to Alberto for giving a wonderful introduction to the world of gamma ray astronomy. I live in gamma rays, I breathe gamma rays, these are my gamma ray glasses, I love them. So I study gamma ray bursts, they're my favorite transient in the entire universe. And today I hope that I can tell you some things about them and you'll be able to tell other people about gamma ray bursts and how awesome they are. So gamma ray bursts are the most powerful explosions in the entire universe after the Big Bang. So I've written here that they're the brightest lights in the dark. That's not necessarily true. The physicists will come get me. Brightness is known for perception, right? So it's how well you can see something, how far away the light source is. But intrinsically, gamma ray bursts are the most powerful objects in the entire universe. They emit more energy per second than anything else in the entire universe. So I think that makes them the coolest, just that alone. But I hope that I'll be able to show you that they're cool for more reasons than just this. So, okay, wonderful. So Alberto mentioned this in his timeline. If you remember the timeline, he mentioned the US Vela satellites. So gamma ray bursts were discovered in the late 1960s by the Vela satellites. And this was sort of an accidental discovery. So the US Vela satellites were launched to monitor the Russians to make sure that they were not testing and detonating nuclear bombs in Russia. And so these satellites were in space to see what they were doing, essentially. And Vela started detecting gamma rays, but not from Earth, from the space. And immediately scientists were confused. They're like, what's going on? Why are we detecting gamma rays from space? And this diagram here, is the first gamma ray burst that was published. And so you can see it's not a very pretty image. We don't get images like in optical astronomy where you see these beautiful colors. In gamma ray bursts, we typically have what we call light curves or count rate plots. So the data that we look at is usually you have time on the x-axis, and then on the y-axis you have something called count rates. So you can think of this as counting the number of photons that interact within your detector. So here you can see there were some peaks, some consistent peaks at the same time in all three of the Vela satellites. And so they immediately saw we have a consistent source that's coming from space. We don't know what it is. All right. So then afterwards, they started realizing this is an astrophysical phenomenon. This is a real source. What are these things? How do we learn about them? So very immediately, we saw that gamma ray bursts were isotropically distributed across the sky. So in this plot, this is an image of the sky, and each of these dots are a gamma ray burst that was detected. And right in the middle here, this would be the galactic plane. So if you remember the image that Alberto showed in his previous talk where you saw the bright red along the galactic plane, this is similar, except you can see that gamma ray bursts come from across the entire sky. They're random. You don't know when they occur. They just occur randomly, and they do not repeat. So you just have one time, it comes from this location, and that's it. So they're non-repeating. Now, learning that they were isotropically distributed, they're random, the next thing that we learned is that they are cosmological. So they come from outside of our galaxy. And we were talking about what is the brightest X-ray source, has the record. Gamma ray bursts have the record for sources that are detected. So the furthest gamma ray burst that's been detected is at a redshift of 9. And so as Alberto mentioned, you have a redshift from 0, which is our present time, up to maybe 14 is what the JWST can see. So that covers almost the entire universe. And so gamma ray bursts can be seen up to a redshift of 9. So that's pretty amazing. You can see them all across the galaxy. And so people like to use gamma ray bursts for cosmological studies too. And so I'll talk a little bit about that later. But knowing that they come from cosmological distances, you can use some equations based on the flux that you get to determine the energy output that gamma ray bursts give. And so the standard energy of a gamma ray burst, the standard luminosity, is what we call 10 to the 53 ergs per second. And so this is essentially a unit of power. You can think of ergs as watts, maybe, if you're more familiar with that. So if you have light bulbs, they give off, I think if it's an LED, you have something like 10 watts, maybe a little bit less, depending on your light curve or your light bulb. But in terms of gamma ray bursts, you can think of this as 100 quintillion suns. So a quintillion is 1 with 15 zeros after it. I cannot even comprehend how powerful that is. People give these numbers and they're beyond my ability to understand. It's the most powerful thing in the entire universe. There's no other object that outputs this much energy except for gamma ray bursts and, of course, the Big Bang. So that's incredible. So when we were able to get distance measurements of gamma ray bursts, this was the output, the luminosity output that they saw. And immediately, theorists were confounded. They didn't know how you would produce such an enormous amount of energy. It's almost unphysical. They were completely confounded. So they had to come up with different theories as to how you could output so much energy. Now, another early evidence for what gamma ray bursts were like were from their light curves. So I showed an example earlier of the first one. And this is just a sample of 6 gamma ray burst light curves. No one gamma ray burst light curve is like another. Every single gamma ray burst light curve is unique. They're all different, and you cannot find no two that are the same. So you have different, multi-peak structures. You can have one peak with a slow decay. You can have multiple pulses that are separated or really short, bright pulses. They're completely different. However, what you can learn from the variations within the light curve, you can go back to your physics, and the variation that we see for gamma ray burst light curves is about 10 milliseconds. So the variation you see within the light curve is about 10 milliseconds. Now, if you use your physics equations, just your standard straight physics equations, that implies a radius of equal to or less than 3,000 kilometers. That's extremely small for an astrophysical object. So that implies you're going to have what's called a compact object, which means either a black hole or a neutron star. So something extremely massive, extremely energetic, but has a small radius. And so we knew these things about gamma ray bursts. They're cosmological. They come from very far distances. They have an extreme energy output. They likely come from a compact object. Now, what do gamma ray bursts actually look like? So this is an artistic rendering of what a gamma ray burst actually is. And it's a relativistic, an ultra-relativistic jet. So meaning when it's ultra relativistic, we mean that it's moving almost exactly the speed of light, almost exactly the speed of light. So typically with gamma ray bursts, you talk about the velocity in terms of what's called the Lorentz factor. So if you know about a special relativity, they talk about Lorentz factors. And this is just essentially when you have material that's moving very, very close to the speed of light. Now, the Lorentz factor for gamma ray bursts, again, is larger than any other object in the entire universe. The Lorentz factor is at least 100, which means that it's moving at least 0.9999% the speed of light. So it's moving very, very, very close to the speed of light. They're very fast, very energetic. Now, there's 3 parts to gamma ray bursts that I'll talk about throughout the presentation, so they're pretty important. First, you have the black hole engine. So this is what powers the gamma ray burst. Now, some people think that a neutron star could also power this, not just a black hole. But so far, as far as observations, we've only been able to confirm that black holes power gamma ray bursts. Now, this black hole can power this gamma ray burst through 2 mechanisms, which I'll talk about a little bit later. This one is showing something that looks like a supernova. So you can have a very special, very massive type supernova that can create a black hole, and this black hole can then power a jet. Now, within this jet, it's essentially a plasma that's moving very, very fast. So in a plasma, you have light and you have charged particles. And in this outflow that's moving away from the black hole, you can have what we can say like inhomogeneous flow. Sorry. So it's not a smooth outflow. You have clumps of particles, and you have clumps here and clumps there, and it's all moving very, very fast. Now, within this outflow, you can develop shock waves. And so you can think of it as if you have an explosion, any type of explosion in our normal life, when you have a bomb, and you have shock waves that go out, and material is going out along with that shock wave. Now, because this black hole can be continuously emitting, you can have multiple shock waves within the jet. And when these shock waves catch up with each other, they can collide and produce an enormous amount of energy. And this is what produces the gamma ray bursts that we see in the light curve. Now, as this shock wave propagates outwards into the interstellar medium, it goes further and further out. It'll start to interact with the gas and the dust that's in the surrounding environment. And this can produce radiation across the electromagnetic spectrum. So from gamma rays, from the highest TeV energies that Alberto was talking about, down onto radio wavelengths, so across the entire electromagnetic spectrum. And this is known as the afterglow. And so all 3 components of this gamma ray burst are essential for understanding the physics of what's going on in each particular system. Because as I said, each light curve is different, each system is different. And so we need observations for the prompt and the afterglow to understand the entire process. Okay, so I'll talk more about space-based observations. Alberto was talking more about the ground-based, but I work more in the space-based gamma ray regime. So previously, I've worked with 2 main instruments, and these are sort of the workhorse detectors for gamma ray burst studies. They're both from NASA, and so you have Fermi and you have SWIFT. And so Fermi was launched in 2008. It detects about 1 gamma ray burst per day. And it's cool for me because I have a phone that gets text messages from the satellite, so I'll get one about once per day. Oh, there's a gamma ray burst detected by Fermi in this part of the sky and with this energy. So that's kind of cool for me. And so the detector on Fermi it's a collection of different detectors. And so with gamma rays, again, they can move through lots of materials. You need something very heavy, very dense, that's going to stop your gamma ray, and so it will interact with the material. And so GBM, or the gamma ray burst detector on Fermi, is a collection of different detectors that detect the gamma rays. And then depending on which detector has more counts, you're able to locate where the gamma ray burst came from in the sky. And so Fermi has the capability to locate a gamma ray burst to about 1 degree. Now for most astronomers, 1 degree is horrible. Most astronomers, they want, yes, see, Sophia's nodding. 1 degree is horrible. You want a localization much smaller than 1 degree. And so if you talk to gamma ray burst astronomers, they do not like Fermi because the localizations are not good. But oh well, that's how it is. So the second workhorse is Swift. And Swift, people love Swift because the localization that Swift is able to achieve is about 3 arc minutes for each of their gamma ray bursts. And now they trade this sensitivity for quantity. So Fermi can detect about 1 per day, but Swift only detects about 1 per week. So you have pros and cons with each, but Swift is really nice because you get the good localization. And this localization is important because what you want is to have observations of the afterglow. And as I mentioned, you can see the afterglow from TeV energies all the way down to radio. And telescopes on the ground, they're not going to go look at the gamma ray burst and get observations unless they have a localization that's small enough for them to look at. 1 degree is too big, so if you have something on arc minute scale, then they can go and say, oh, we'll look at this gamma ray burst. So yes, essentially what I'll be talking about are observations from both of these telescopes. Okay, so we talked about some of the basics, but one main characteristic of gamma ray bursts that I'll talk about a lot is the duration. There are 2 types of gamma ray bursts that people have talked about since they were first discovered, and that is short GRBs, gamma ray bursts, and long GRBs. And the divider between these 2 populations has been declared at 2 seconds. Now, this is a distribution where you can see the duration, or what we call the T90, which is 90% of the flux. This is just a measurement that we use. But you can think of it as the duration of the burst. And you can fit 2 different distributions to this entire plot here. And you can see that the divider at 2 seconds is just, it doesn't even necessarily look like it's in the middle. This is more of a historical divider. But we see that there are other properties that sort of combine GRBs into short and long. So for example, longer GRBs, they have a softer spectrum. It means they have lower energies. They're seen at lower energies than the short GRBs, which have a harder spectrum. They're seen at higher energies, slightly higher. The types of galaxies that you find long GRBs in are different than the types of galaxies that you see short GRBs in. So for long GRBs, you see galaxies that have low metallicity, there's more star formation, whereas with short GRBs, you typically have older stellar populations, not so much star formation, but in different types of galaxies. Also, when you look at the distribution of GRBs within the galaxy, long GRBs tend to be very close to the center, where short GRBs tend to be further away from the galactic center. And given this information and previously about the energetics, people came up with 2 different origins for each of these gamma ray burst populations. For long GRBs, they said that the origin was from type 1bc supernovae. Now, 1bc supernovae, these are very massive stars that when they go supernova, you do not see hydrogen because they've burned through all of the hydrogen. You do not see silicon because they've burned through all the silicon. They're very massive stars. The types that you see with gamma ray bursts are usually rotating very rapidly. It's a very rare type of supernova. For the short GRBs, people theorize they came from neutron star mergers. So this is when, again, you have very old stars, neutron stars, that are locked in a binary orbit, and eventually they collide and they can release an enormous amount of energy. They can produce a black hole, which will power a jet and produce a gamma ray burst. So this was theorized. And very quickly, very early on, we were able to see the connection between supernovae and long gamma ray bursts. So this is a plot of, this is again a light curve, but this is for the optical regime of the afterglow for GRBs. And where you can see a power law decay for many of these GRBs. This is from the afterglow. And then around 10 days, you'll see this bump. And essentially, this is when you have a supernova. The gamma ray burst comes forth, it's giving a lot of energy, but then over time, the flux starts to go down, it's decelerating, it's getting weaker, and then all of a sudden you're able to see the supernova bump. And so this is what we call a supernova bump, and this is for, we've seen this for multiple gamma ray bursts, long gamma ray bursts. And you can see this, an example of this in an optical image here. So this is an area where we saw a gamma ray burst, and this tiny little dot, that's the supernova that we saw 10 days after the gamma ray burst. And so these were very robust connections between long GRBs and supernovae. So people thought, okay, supernovae produce gamma ray bursts, all long gamma ray bursts come from supernovae. I'll show you how that's not true later. Okay, now for short GRBs and the connection to binary neutron star mergers. This is the gamma ray burst. It's called GRB, gamma ray burst, 170817A. That means it occurred in 2017 in the 8th month, so August, on the 17th day, and A means it was the first gamma ray burst of the day. It is the most famous gamma ray burst in history, and if you talk to anybody about gamma ray bursts, this is the one that you need to know. It is the most famous, and it's incredible event. So I'll tell you why, and then I'll tell you a personal story about it. So, well, first I'll explain the data, and then I'll tell you why it's important. So this is the gamma ray burst data. So again, you have the light curve where you have time, and then you have your counts. Now this was seen in the Fermi spacecraft in 2 different energy bands, so just in 2 different energy ranges. You can see a peak, and you can also see it in another satellite that's called Integral that had a peak at the same time. What's special about this burst is that it was also seen 2 seconds after a detection of gravitational waves. Gravitational waves are a disturbance in space-time. It was theorized by Einstein back in 1915, a part of his theory of general relativity. When he was coming up with his theory of general relativity, something that popped out was gravitational waves, and he was like, okay. But the sort of energy, the flux that you would get from gravitational waves was too weak at that time for him to make any sort of tests. So it took up until 2015 for humans to build detectors on Earth that would be sensitive to gravitational waves. So now gravitational waves are detected all the time, mostly from 2 black holes. But gravitational waves can also be produced from 2 neutron stars that are in a binary orbit, and they can collide. And they can disturb space-time so much that they produce these waves that are detectable on Earth. Now, this signature here is the detection of the gravitational wave from the binary neutron star merger. And you can see this is called a chirp. So you have time here, but instead of counts, you have frequency. So if you think of your 2 stars, they're orbiting around each other at some frequency. As they get closer and closer, they're going to go faster and faster. The frequency is going to increase. So as they get closer and closer, they eventually merge and collide. The frequency is going to go way up as they collide. And so this is why it's called a chirp. Now the delay between these 2 signals was about 2 seconds, and they came from about the same region in space. This was an amazing detection for multiple reasons. I've listed only a few of them here, but this was the first GRB that was observed with gravitational waves. That was the first thing. This particular type of detection is known as multi-messenger astronomy. And I said this is the second one in history. So multi-messenger astronomy is when you do astronomy with more than just light. So for example, light and gravitational waves, or light and neutrinos. So the first multi-messenger detection in history was actually with a supernova that produced neutrinos. And so people detected the supernova and they also detected the neutrinos. And what's important with multi-messenger events is that you can learn 10 times more science than you can with just one messenger alone, messenger being light, gravitational waves, or neutrinos. You can learn a lot more. So analogous to when you see, for example, images of the Milky Way. You see it in gamma rays, you can see it in optical, you can see it in radio. Each of those different wavelengths tell you something about the galaxy. And combined, they give you a fuller picture of how the galaxy works. In the same way, multi-messenger detections tell you more about what's going on than if you just have information from one alone. So this was an incredible observation that occurred. So again, it was the first confirmation that binary neutron star mergers, the two neutron stars, can produce short GRBs, just like theorists had predicted. So like, check, okay, that worked. It was also the first detection of a binary neutron star in gravitational waves. So this was the first one that they had seen in gravitational waves. So it was also important for that. It was also had a confirmed detection of a kilonova, which I will talk 2 slides from now about what that is. Connected to the kilonova, it was the first evidence of what's called R-process nucleosynthesis. I'll tell you about that in 2 different slides. But essentially, that's how you get gold, silver, all your heavy, heavy elements in the periodic table. And then lastly, we were able to constrain the speed of gravitational waves. So this is essentially a test of general relativity. So Einstein had predicted his theory of general relativity. Gravitational waves had popped out. And if his theory was correct, gravitational waves should propagate at the speed of light. So comparing the time of arrival of the gamma rays to the time of arrival to the gravitational waves, we were able to place a constraint on the fractional difference between gravitational waves and gamma rays, or light, to less than 10 to the negative 15, which is a really, really, really small number. So we can say gravitational waves travel at the speed of light, and Einstein was right. And I think that's really cool. So, all right. So continuing to talk about this particular GRB, it was interesting for more than just multi-messenger astronomy alone. It was interesting on its own right as a gamma ray burst. So this is a plot of the redshift, or the distance, versus the luminosity. And this is different gamma ray bursts that have a distance measurement. So the blue ones are the long GRBs, the orange ones are the short. And the one that we detected, 170817, was right here. It was super close, but you can also see it was super, super dim. It's very dim. Why would that be? So there were some different theories about how you could have such a weak detection. So the first one was, okay, you have this jet that's propagating outwards, and maybe some of the emission got relativistically beamed into our line of sight. So we were over here, the jet was going this way, and due to some special relativity things, we got some emission over here. But if you compare that to the energetics of the GRB, this theory actually doesn't work. So it wasn't that. The second theory is that you have something called a structured jet. So essentially, even if the jet is not pointed at you, it has some gradient in the energy and the density as a function of angle. So if you think of like you're holding a water hose and you put your thumb on it, and the fastest part is going straight, and then there's a tiny little bit that's going slower as a function of the angle of the water. This is akin to that. The third theory was that you had a straight jet, and then you also had some other emission that's called a cocoon. We won't worry about it, but essentially it's a slower type of transient that comes out of the jet as a secondary component. And so then there were some observations from the afterglow. This is a plot showing that versus time. So this is time in days, and this is the flux. Essentially, this blue line here is the model of the structured jet. So, and these other lines here are models of the cocoon emission with the jet here. So you can see that all observations fall along this line, and so we are able to say that yes, this was a structured jet. It was not pointing right towards us, but at an angle away. And for gamma ray burst people, this was really exciting. I will admit that nobody else in the astronomy world was really excited about this except for us gamma ray burst people, but for me it was really cool. Okay, so now we know that gamma ray bursts can also have some structure. We can see them even though they're not directly pointed at us. And now, so the thing that astronomers were really excited about, not the gamma ray bursts, they were excited about the kilonova. So a kilonova is a transient that's been theorized for decades and decades as a place where you could produce heavy elements. So this is the periodic table here, and you can produce elements up to iron in some types of supernovae. And it was thought that maybe you can produce elements even heavier than iron in some supernovae, maybe in binary neutron star mergers. And so the neutron star mergers are in the orange color here, where they thought that binary neutron stars would produce these heavy elements. And you can do that through the kilonova transient. So essentially, you have these two neutron stars that are smashed into each other, and they release a whole amount of neutrons. And so in this dense environment where you have a lot of neutrons, the neutrons are bombarding each other really quickly. And so they're able to essentially fuse together and build up heavy elements, but it's so dense that they can't decay into other elements. They just keep building up until the transient as a whole starts to cool down, and then they can decay and produce this optical light that we see that we call a kilonova. So again, it's this process where you have a lot of neutrons, they're smashing into each other, they build up to heavy elements, and then they release this optical or even UV light that we call a kilonova. And so this is essentially where you can see gold, silver, platinum, tungsten, all these interesting heavy elements where they're produced. This is the only source in the entire universe where these elements are produced, which is pretty cool. Okay, so that was the first detection of a GRB with a kilonova. And we have had a recent detection of a second GRB with a kilonova. So these are very new detections. And so this one was GRB 230307A, so it occurred in 2023. And you can see the red dot here of the kilonova. And JWST was able to take a spectrum of this kilonova, and this is what it looks like. So essentially you have, this is your wavelength of light zoomed in, and this is the brightness of your observation. And so you see a bump here where tellurium would be expected at this particular redshift. And so this was, again, evidence for a kilonova and the production of very heavy elements. But what's interesting about this GRB, other than just the kilonova, is that it's a long GRB. It's not a short GRB. So in that plot that I showed you, astronomers assumed that all long GRBs come from supernovae, all short GRBs come from binary neutron star mergers. And the divider is at 2 seconds. But this GRB is much longer than 2 seconds, and it has a kilonova component. So everything that we've known or thought we knew about gamma ray bursts being short and long and connected to these different transients is wrong. And we have another example. So there's 3 detections of GRBs with kilonovae. 2 are long GRBs, which is interesting. So this is another GRB that's definitely long. You can see the duration here is at least 50 seconds, maybe out to 60 or 70 seconds. When you plot all of the GRBs that have been detected by SWIFT, you can see it's right in the middle of the long GRB population. This is duration versus hardness, essentially so you have higher inner GRBs here, lower inner GRBs here. So it's right in the middle of the long GRB population, but when you look at the observations of the GRB, it fits with the kilonova model. So these straight lines here are just the afterglow, and these wavy ones that you see here are the kilonova model. And it's kind of hard to see because there's a lot of lines, but all the observations fall along the kilonova model, not just the afterglow model. So this was another example showing how our supposed theory is wrong. And we have another example, except this is a short GRB that has a supernova component. So again, at the beginning, I showed how you had these decays, and then you had a supernova bump that started about 10 days. So this is a GRB that has a duration of about 1.5 seconds. It's a short GRB, but it has a supernova bump just like any regular long GRB does. What's interesting, if you look closer at this GRB, if you look at its energetics, so this is energy, total energy, versus the peak energy. This is the long GRB population, and this particular GRB is the red dot, and it's right in the middle of the long GRB population. So it seems to fit with long GRBs, but its duration is completely different from what we'd expect. So there are some ideas about why this happens. So for short GRBs, they think maybe you could have something like a thick stellar envelope. So when the star goes supernova, there's a lot of material that's pushed out away from the black hole that the jet has to push through. And maybe it's just so thick that the jet gets slowed down, and so maybe it takes a long time to actually pierce the jet. For the short GRBs, for the short ones that look like long ones, some people think that they could be powered by a special type of star called a magnetar, which has a really high magnetic field, but no observations have confirmed this yet, and honestly, people don't know. They really don't know. They say this in papers, but there's no observational proof. So really, we don't know. And that's what I'm showing here. So in the last, I would say 5 years, what we've known about gamma ray bursts as far as their duration and being able to classify them to supernovae and binary neutron star mergers, we just have no idea now. And so we have to go back to the drawing board to understand what's really going on with these GRBs. So the last GLB I'll talk about is more of an exciting one. This has nothing to do with the duration issue. This is GRB 221009A, and this really was the brightest burst ever. So it's called, oh, no, don't show it yet. Oh, it's going the wrong way. I don't have any in the back. I was pressing the right button, I swear. Okay, so this GRB is known as the boat. So does anybody here know what the goat means? If someone says you're the goat or this is the goat. So it means the greatest of all time. So like they're the baddest, they're the original, like coolest thing ever. Now, when astronomers were talking about this GRB to reporters, they're like, this is the brightest burst that's ever occurred in all of time. And the reporter was like, oh, it's the brightest of all time. It's the boat. And so, so essentially a reporter named this GRB as the boat. It's the brightest of all time. Here's a picture of distance and the energy, and you can see it's a clear outlier. And this plot here, this is other GRBs. These were the previous record holders of the brightest of all time GRBs. You can kind of see, I hope you can see it, but there's a faint sort of purple line here. Essentially, when the gamma ray burst detectors in space saw this particular gamma ray burst, this was all the flux that they could see because the gamma ray burst saturated the detectors. Essentially, it's as if you had like a flashlight so close to your eye, you just can't see. And so it was so bright, it completely saturated the detectors. What's really interesting is that Alberto was talking about how gamma rays can come into the atmosphere and they produce particle showers. This gamma ray burst was so bright, it ionized the atmosphere so much that it created a disturbance in the atmosphere, similar to how a solar flare could come and like disturb electronics within the atmosphere. This gamma ray burst was so bright that it did that. So it's the brightest thing ever. And this is it should be an animation. Okay, yeah, this is an animation showing the previous record holders of the brightest GRBs of all time. That one's actually not a GRB. It's a different transient that we thought was a GRB, but it's not. This one was known as a monster, an unusual monster at the time. This one was the first GRB with a TeV detection, which Alberto studies. And this one had an optical flash so bright you could have seen it with your eye. And then you have this one here. So it's an incredible GRB compared to all of the other ones. We've detected over 10,000 GRBs since the 60s. And so this is the brightest one that we've seen so far and likely to see in our time. Okay. So the last two things I'll tell you about this burst that are quite interesting. So Alberto was talking about how with GRBs you can detect them in TeV energies, which are the highest gamma rays that you're able to observe. So with this detection, or GRB, they were able to detect up to TeV energies with ground-based gamma ray observatories. This is interesting because physicists didn't think it was possible, really, to have this detection at 10 TeV for an object so far away. So this was at a redshift of about 0.15, which compared to the entire history of the universe, it's not that far away. But for what you would expect for a TeV emission, it's quite far away. So this is what was actually detected, where you see this drop off here. And the reason that you don't expect TeV emission is you expect that these high energy photons will interact with the background gas and dust and essentially just reduce the flux. And so when you account for that, for the interactions with the gas and dust, you can reconstruct what the intrinsic energy would be. And this is the flat lines that you see here. This is interesting because a lot of physicists wanted to come up with new physics for how this detection might be possible. At the last conference I was at, physicists were arguing about whether they needed new physics or whether standard physics with some little tweaks could explain this. So for particle physicists and cosmologists, this detection was very interesting. And lastly, another thing that was unexpected but interesting with this GRB is that as it passed through the clouds, the gas and dust clouds surrounding our galaxy and going through the galaxy itself, you can get light that interacts with the gas and dust and it reflects towards Earth. And at each of these dust clouds, you can get a ring of emission. And so by studying the pattern of the rings and how fast they expand with time, you're able to study the distribution of gas and dust around our galaxy. So people who study our galaxy were able to use this information to learn more about the surroundings of our own environment. So these are two very interesting, sort of unexpected detections that happened with this GRB. So in all, it was just an incredible detection. The last slide that I have. So I'm also working, in addition to Fermi and Swift, I'm also working with a new mission called SVOM. It is a French and a Chinese mission that launched on June 25th. So it very recently launched. And it is dedicated to the study of gamma ray bursts. That is its primary mission. And what makes it special compared to other satellites is that it has these multi-wavelength capabilities. So it has telescopes that go from gamma rays to optical wavelengths on board the satellite. And it also has dedicated ground follow-up. So one of the things I mentioned early on is that telescopes don't want to point towards GRBs because the localizations are too large. Well, these telescopes are dedicated to pointing towards the GRBs that SVOM detects. And so that's really, really important because we can get very early optical observations, and this could help astronomers better understand the physics of gamma ray bursts and of kilonovae. So look forward to hearing more about SVOM. I will say that we've already had our first gamma ray burst trigger. It's not like public information, but we're already detecting gamma ray bursts, so that's really cool. And that's the end of my talk. Thank you. I'll leave the conclusions here.
Thank you so much, Rachel. Do we have questions from the audience?
Hi, thank you very much for the nice talk. I have two questions. The first is, I mean, talking about this, but I don't know if I forgot it completely. Can I think of gamma ray bursts as a sort of collimating light? So like a laser beam, something like that. So if it is the case, how can you detect it? Because if it goes to a direction which is not facing the Earth, you will not detect it. And if it goes to the Earth of one of those space telescopes, you have 10 to the 53 Earths of energy. Does it burn it, or how does it work?
Yeah. Oh. Wait. Okay, yes. So gamma ray bursts are jetted. You can think of them as lasers, as beams. So it's true. We do not detect them unless they're facing towards us, unless they're coming towards the Earth. Now, if gamma ray bursts are very close. For example, with the most famous gamma ray burst ever that was seen with gravitational waves, if there's some spread to the jet, then if it's slightly off-axis, then we can see the off-axis emission. But as you saw, the energetics were much lower than if you would see it as it was pointed straight on. Now, I will say the figure that I mentioned, 10 to the 53 ergs per second, that is when you assume isotropic emission around the black hole. Now, we typically assume this because we do not have jet measurements for each gamma ray burst. We only have jet measurements for probably 1% of gamma ray bursts. It's very small. In order to do this, you need to observe the gamma ray burst for tens of days until you see the signature of what's called a jet break. It tells you essentially how big the jet is. So for the sake of our population, we assume isotropic emission. Now, when you consider the jet energy, the luminosity goes down by a factor of like 100. So the typical gamma ray burst energy, when you consider the jet, is probably like 10 to the 51 ergs per second. But it's still the brightest object in the entire universe. So, yeah.
Hello. Okay, so Fermi, you were saying was like less accurate with like or precise with location.
Mm-hmm.
So I'm curious, like, is there like drama or debate when people have findings with that data? Like, for example, I saw the most famous one, that was Fermi data. Like, is anybody like, well, do you really know if the gravitational waves are right there? Do people debate that?
Yes. Yes. So Fermi localizations are typically quite big. However, with the gamma ray burst observation, it's a little bit different. So gamma ray bursts, as I said, they're only seen about once per day. So if you compare the rate within an area of the sky, and then you compare that to the rate of detecting a binary neutron star merger in that same portion of the sky, there's also a localization from the gamma ray, from the gravitational waves itself. So when you combine the localizations, you combine the time offset and the rates of these things, and the probability of association is actually quite good for this event. But it's true that with other types of events, there is drama. So for example, when we detect an object that might be a magnetar, and it would be a new source. So for example, if we detect a new source, people are like, oh, maybe it's not there, maybe it's slightly over here. So they don't really point their telescope. This list, okay, Fermi saw something, but we're not going to do anything about it. So really, to have more observations, you have to have an observation from Swift, which has a much better localization. So again, it's sort of the quantity over quality thing. Yeah.
Questions?
When you mentioned that after this work discovery, in some conference, people start talking about the idea of formulation physics. Can you give more details about which ideas they propose or which side of physics they propose to reformulate?
Yeah. Yeah, so I can't speak so much to that. I know that they wanted to, so for example, with this particular observation, it had to do something with Lorentz invariance. And so theorists were thinking, well, maybe it's not true in a certain set of circumstances. I'm not exactly sure of all the details because I'm not really involved with cosmology or particle physics. But some theorists were claiming that there would need to be tweaks to the standard model in order to account for this observation. But as I said, there were other theorists who said, no, we can come up with scenarios where this observation makes perfect sense. So unfortunately, I'm not well versed enough in those theories to really give more details about them. But I encourage you to look up this GRB because it sparked a lot of debate in the community.
More questions?
I have two questions. The first is, in the naming convention, what is the largest letter that they've gotten up to for a single day? And then the other is why, is there a reason why these things are always jet-like structures? Like why does every image you see of this stuff jets coming out of the holes and that's some shock?
Okay, so for the first one, the largest letter that we've got up to is E. So it's 5 GRBs per day. So yeah, but that hasn't happened in a really, really long time. Recently I've seen D, but yeah, E was like a one-time thing. So there are two reasons really for jets. So in general, when you have an accretion-powered outflow, essentially you have the magnetic fields that are getting twisted up around the black hole. And as the charged particles travel along the magnetic field, the way that this sort of occurs with the rotation is in a jetted sort of formation. Now, an additional reason is that when you have charged particles that are moving around a magnetic field that are giving off something called synchrotron emission. Synchrotron simply means that your particles are moving around the magnetic field and giving off light. When you have charged particles that are moving close to the speed of light, that are also moving around the magnetic field, you get the synchrotron emission is beamed forward into a sort of cone. And this just comes out from the relativistic physics. So it's, you know, and similar to how time dilation and length contraction pops out of relativity. When you have particles that are moving close to the speed of light and moving around a magnetic field, they get beamed into a cone. So you have both of these physical processes at play that kind of encourage jet-like behavior.
More questions?
I'm wondering something, but it's like very technical. It's like a detection bias in the sense like you are saying that you find many sources that were not explained by the distribution, but it's maybe because we are easier to detect those ones rather than them being more common.
Yeah, so for shorter GRBs, this can be an issue depending on the instrument because you need a high time resolution in order to capture the shorter GRBs. For longer GRBs at the other end, this is also a problem because if you have longer GRBs, they can be weaker, they can also blend into your background. And so when you're doing your detection algorithms, it's a bit difficult to pick up these GRBs. Now, that being said, for example, SVOM is more sensitive to these longer GRBs. They're called ultra-long GRBs, and they can occur for minutes rather than seconds. And so it's the detection algorithms are tuned to GRBs like this. And then you have other instruments that are in space that have a very fine time resolution, so they can pick up the shorters. So you do have instrument biases in this distribution. But for the I would say the bulk of the population, this is what you see.
Thank you. So do we have time for one more question? If not, thanks so much to Rachel and to Alberto and to everybody for coming. And also thanks to the others for letting us be here and enjoy science and beer. So enjoy your afternoon. Yeah. Woo!